Hello viewers, we are Group M20 and we have been tasked with determining a suitable material to manufacture and process a drill bit. A drill bit is a tool to remove material, typically metal, plastic, or wood, from a part. Drill bits are commonly used by a hand drill, drill press, turning on lathe, and milling. Current standard drill bits are made of high-speed steel, cobalt steels, and ceramic carbide. To narrow this problem down into something more digestible, we have defined a specific case. We are drilling a 1-inch diameter hole into a 1-inch thick plate of heat-treated 4340 steel. This case allows for two extrapolations. Since 1-inch diameter is a large hole, smaller holes should impart equal or less force on the drill bit, making the selected material acceptable for smaller sizes. Next extrapolation involves the hardness of the steel chosen. Since heat-treated 4340 is very hard, drilling into softer materials should put less wear on the drill bit, making the selected material acceptable for softer materials. Essentially, the extremes of hardness and drilling forces was assumed, so that the material selection can be extrapolated for all material and hole sizes. Note that this material selection will not consider the types of bits required for wood or composite materials.
Two assumptions are made in this material selection process. The first is that the drill bit can be somewhat accurately modeled by a cylindrical rod. Even though the surface area and moment of inertia of the actual geometry is less than a full cylinder, it was taken into account by modeling the reduction in area by constant terms that were approximately 0.6. This should provide a somewhat realistic model of the geometry without involving unnecessarily complex math. The other assumption is that there is no shear loading on the drill bit. There is no force acting perpendicular to the axis. The assumption is valid for the defined situation, but may not be representative of real-world applications. Even though it is recommended to drill straight perpendicular to the material, in reality the drill bit may slip or walk, causing shear force and bending moment in the drill bit. Under normal operation, a drill bit must have a high hardness to be able to cut heat-treated steel such as AISI 4340, which has a hardness of 570 Vickers. Therefore, the drill bit should at least have a hardness of 850 Vickers. It must withstand 1,200 axial load without failing by buckling or crushing. The maximum deflection in the axial direction must be less than 0.05 mm, which is approximately 0.25% of axial strain. The torque in through the drill bit is approximately 10 Nm. In addition, drill bits will have high operational cycle, which may cause the drill bit fail under fatigue. The drill bit should also have a high fracture toughness. These concepts were not quantitatively determined, and instead the relative differences between materials formed basis for rankings. There are other non-functional constraints such as edge retention, corrosion resistance, sharpenability, and cost.
The material selection process began with determining an appropriate MPI to suit the quantitative requirements. Since the action of removing material is determined by torsional resistance in the drill bit, high torsional stiffness is required. This would reduce the compliance when drilling. Thus, to quantify the stiffness, the primary constraint was to maximize the torque at the tip of the shaft for any given angular deflection. Shown on screen is this primary constraint. The functional requirement is linear deflection in the axis of the drill bit. This is given by the deflection equation. These equations can be related through the free variable L, and the resulting equation can be massaged into something that fits the form of an MPI. A point on the line can be solved for, and the MPI can be applied in CES EduPack. Since G and E are relatively linear in isotropic materials, this stage ended up removing approximately 700 of the 4,000 materials. Another MPI was considered for buckling failure. Details of this MPI can be found in the report. The next stage is applied known limits to the material base, the 850 hardness Vickers, and lowest max operating temperature of 550 degrees Celsius. This reduced the number of choices to fewer than 200. The next two stages involve applying limits for indeterminate quantitative measurements. Since toughness and fatigue strength did not have hard numbers, each property was plotted against costs, and the material group with the best ratio was selected. This was done for toughness and fatigue strength. Finally, the material choices were reduced down to tungsten carbide and tool steel groups. Tungsten carbide may be a good material choice for drilling into hard materials, but it is excessive for this case. Therefore, tool steels were the better choice. Among the final remaining tool steels, M42 was selected due to the availability of published data for heat treatment and processing.
The first step of producing drill bits are cutting the raw materials to an appropriate length. Then heat treatment process will take place. The steel rod will then be placed into a hot molten salt bath or a furnace that is set to authorization temperature. This prepares the rod for quenching. Quenching can make the steel rod much harder but also more brittle due to the percent of martensite. Therefore, tempering is required to increase the ductility of steel without significantly compromising the hardness. More about the heat treatment process will be discussed later in the video. The next step is grinding, polishing, and sharpening, which is cutting the fluid into the steel rod, preparing the surface for coating and sharpening the edge of the fluid. Coatings are important to protect the drill bits and increase the lifespan and the hardness. It can be done by various ways, such as painting. In order to produce desired properties, heat treatment is an important process. The first step is authorization. The steel rods are placed into a salt bath or a furnace in a range of 1150 to 1290 Celsius. This is the authorization temperature for typical high-speed steel, including M42, and hold the temperature for 5 to 6 minutes. Right after the authorization, the authorized rods are quenched into oil. This process will significantly affect the microstructure and the final properties of the material, so it must be controllable. The quenching process first involves oil quenching the steel down to roughly 540 to 595 Celsius in a matter of seconds, then normalizing the hot steel rod to ambient temperature over an hour. This process is followed by tempering, which takes far longer. Multiple rounds of tempering might be required to achieve the optimal properties. This is typically done 2 to 4 times for high-speed steel. Each round of tempering involves holding the steel for 2 to 4 hours at a minimum temperature of 540 Celsius, which must be lower than the critical temperature. The steel must then be air cooled to surrounding temperature before the next tempering cycle. This is the phase equilibrium diagram for iron-carbon alloy, and the red line indicates the phase transformation for 1.1 waste percentage of carbon, which is appropriate carbon concentration of M42 steel. This blue line circle on the screen shows appropriate authorization temperature about 1417 K, which equal to 1200 Celsius. This reinforces the authorization temperature established in the heat treatment schedule, 1150 to 1290 Celsius. The holding time of 5 to 6 minutes is determined by the size and the geometry of the material. In this case, drill bits are relatively small, so the time it needs is short.
Shown on screen is a continuous cooling transformation diagram for M42 steel. It shows the microstructure transformation under different cooling rates. The cooling rate of oil quenching is about 30 degrees per second, so high concentration of martensite structure forms from quenching. Martensite is a needle-like structure that impedes dislocation movement and significantly increases hardness. This increased hardness also induces an internal pressure from the differential cooling rates, which also increases the brittleness of the steel. This brittleness can be resolved via tempering.
Tempering is a process that heats a metal until trapped metastable atoms causing internal stress can diffuse out of the BCC ferrite lattice. This reduces the internal stress. Shown on screen is a tempering diagram for 2 hours for AISI M42. In the diagram, the peak hardness is 66.5 HRC at a tempering temperature of 540 for 2 hours. This reinforces the selected heat treatment schedule. For a drill bit, coatings are important. There are 3 main types for drill bits: zirconium, black oxide, and titanium. Titanium coatings are typically the hardest and provide the most protection, thus will be the ideal coating for this case. Specifically, titanium aluminum nitride has a high heat limit and increases edge hardness, which will prolong the lifespan of the bit. TiAlN is the hardest coating, thus will be the optimal for this case. In cases of drilling into aluminum, TiCN will be preferred.
After research and analysis, the desired material for a drill bit is AISI SAE M42 steel with the titanium aluminum nitride coating. This alloy has high hardness, high edge retention, and heat resistance. MPIs and other limits were used to determine the material choice. This steel is heat treated by quenching from austenite, then repeatedly tempered for greater toughness. Other tool steels had similar properties, but M42 was chosen for the abundance of published data available. Tungsten carbide may also be a consideration when drilling into harder materials, but carbide is more brittle and expensive.